Hello there. So, I would like to talk about Lie theory. Um, Eventually, I would like to talk about Lie algebras. So, there's Lie groups, and then there's Lie algebras. And let us see here. There's this. I'll explain more about what all this is. But part of Lie theory is that there's this classification of Lie groups, or at least these simple Lie groups, and then there's these exceptional Lie groups. And so overall, I mean, as far as things are concerned, as these things are concerned, there are not that many of them. It's not an overwhelming amount. I mean, there's these four families of classical simple Lie groups, and then there are five exceptional ones, this G2, F4, E6, E7, E8. And actually, there's these there are these unification theories in physics based on E8. That maybe everything in the universe is explained by E8. But these other ones are also very important. F4, G2, E6 are interesting in physics, and as well as all the classical Lie groups. Now, of course, I need to explain what a Lie group is. That will take a little bit of time. I have talked about it before here. However, I have a little more of a faster one because I was writing everything out and it took a long time. It took like an hour when I did it before. So I have stuff prepared to make it a little smoother, a little faster. I suppose I should talk about prerequisites. Definitely calculus and understanding about matrices those are the major prerequisites. There's technically, if you want to understand it, like in terms of fully understanding it when you read a textbook or something, you do need actually to know topology. However, we can gain an intuition for things without having taken a course in topology. Okay. And what is all this stuff about? I guess I want to sort of give you an interesting fact to try to sort of hook you in, for at least for some of the audience, about why this stuff is interesting. And so there's this very interesting fact that I think is one of the most interesting facts in all of mathematics. Where should I write it? I'll write it up here. It is that E, that's a transcendental number E, sometimes called Napier's number, raised to x times a matrix, which is this matrix. Wait for it, it's going to be interesting. We're treating x like a scalar, just multiplying through the matrix. This actually is going to be equal to cosine of x, sine of x, negative sine of x, cosine of x. So this 2 by 2 matrix here. And this matrix is exactly what you would use to do rotations in 2 dimensions. So if you're doing a game or you're doing math and you're rotating in 2 dimensions, you can use this matrix, plug in any angle into x. You can plug in pi over 2, pi over 4, whatever angle you want, and it will, then you multiply this times some matrix. Now this is no longer equals because I'm writing this on the right hand side, but if you take this and multiply it times this matrix, or sorry, if you take, well, technically this is a matrix, but usually we refer to this as a vector. So you have some x and y position. I'm using x in 2 different ways now, so let's just put like a knot here so that it's representing actual points, okay? These are just labels. but we have an X and a Y position somewhere in 2 dimensions. And I guess, maybe I should have used a theta here instead, but it doesn't really matter. We are rotating in 2 dimensions by some amount, X here. And so every point, any point can be plugged in here to this vector, and then you can rotate by some amount. So this is, if you study how to rotate things in a game, this will come up, especially 2D. This is the matrix to do that rotation. And that's very useful. So for me, when I see this, okay, this is the rotation matrix. And by the way, you can, instead of a minus here, you can make the minus here. And that's just rotating in the opposite direction. That's all. Okay, so this is like the rotation matrix. This is a big deal. And then what is all this shenanigans over here, right? What is this? And it turns out that this whole picture here is more or less identical to this e to the I theta business. This also will equal some amount of rotation. You can make this sort of correspond to a rotation, but this, you can't directly write this as a matrix. What you can do is you can say that this is equal to some, we can actually, this is going to look silly, some amount of I, right? There's just this is just an exponential map. But more generally, I'd like to do it like this. I'll just do a plus bi in the exponent, okay? And this will be equal to some complex number, c plus di. It's just an exponential map. It's the complex equivalent to talking about e to the x power in general. There's some function. When I say map, if you don't know what I mean, just think function. So here's e to the x, right? But in the world of complex numbers, you can also do this. And the important thing is that there's sort of a closure going either way. So no matter what complex number you plug in on the right, there's some e to some complex number. So we could just have written this as some arbitrary complex numbers like alpha and beta, where alpha and beta are complex numbers. There's, for every alpha there is some beta, and for every beta there's some alpha. There's a mapping there. Okay. And so that's the story of complex numbers, but this story is basically isomorphic to this situation. So by isomorphic, meaning basically it's the same structure. Okay? So imagine it's sort of like when you study geometry and you have similar triangles or similar shapes. They're not exactly the same shape, right? They're in different places or something. Or rather, not just similar, but congruent shapes. You have 2 different squares and they're congruent to each other. Well, you wouldn't say that square 1 equals the other square. They're not. They're 2 different squares, but we say they're congruent. That concept of isomorphism is basically the same idea. We're saying that things are different, but they're basically the same thing, right? They're just 2 different versions of the same structure. So what that means is that if you're uncomfortable with the whole story of imaginary numbers, so-called imaginary numbers, complex numbers, you don't have to think about all that. You could do things with this e to the x times this matrix. And again here, we could put a plus here and a minus here, and this would rotate in the other direction. It would become like this, plus, minus here. So I forget which is which. I think this is rotating counterclockwise, which we often call the positive direction, and the other one is the other one. But yeah, so I thought this was amazing because if anyone has a deep feeling of not trusting the whole story of complex numbers, makes you feel uneasy, well, you can sort of translate everything into the story of matrices. Now, the story of matrices makes things, in many cases, much more complicated to write and to think about. So, I mean, you're always rotating something here. At least in this case, we're just talking about 2 dimensions. But the story is basically the same in the n-dimensional case, because even if you have like 5 dimensions, you basically pick 2 to rotate in. Well, if you're rotating in a 5-dimensional space, there will be some plane. I don't know, some plane here. There's your plane embedded in this 5-dimensional space. So there's a 2-dimensional subspace within the 5-dimensional vector space, and you're rotating in there. So no matter what the n for an n-dimensional vector space where n is greater than or equal to 2, for every rotation, as long as that rotation is not sort of shifting its axis, so to speak, it's not changing into a different kind of rotation, as long as it's sort of like if you have constant rotation over time or something, there will always be this plane, this planar subspace, a 2-dimensional subspace within the higher dimensional vector space that defines the rotation. So basically, any rotation will boil down into this 2-dimensional picture. Okay, so it's very fundamental, and I just find it great that we have this other way of thinking about this stuff. And then, well, you wonder, well, this was interesting, this particular matrix, and so I'm going to, by the way, demonstrate that this is true. I haven't said how this is true and why. I have done out this calculation before here, but I'm going to do it a little faster later today within this video. So I'm going to demonstrate that this is true. But yeah, so when you realize this is true, well, you start thinking about other matrices that we could put in here. What is special about this matrix? And so on. And so this is sort of, to me, this is the great, at least this is one way to approach it, that this is a great motivating example for Lie theory. That if you discovered this particular fact, which is pretty amazing, then it like opens a whole new world. Opens a whole new can of worms, Pandora's box, whatever you want to call it, where there's all this stuff to investigate. At least that's how I think of it. So that's sort of a motivation for getting into Lie theory. And if you did that for a long time, you would discover, well, this is the classification. These are using different matrices and things. We can create different Lie groups. Now, what exactly is meant by a Lie group? Well, the picture here is that you're always sort of exponentiating these. Well, you're always sort of exponentiating these matrices, except that these exceptional Lie groups, these 5 from G2 down to E8, these cannot be expressed just with matrices in the normal way, at least. And it turns out to talk about those, you actually need these things called octonions. We'll talk about it later. But for the classical Lie groups, you can express them using matrices. You might need to do matrices with quaternions, but I think you can break that down further down into matrices. So basically, yeah, we can use matrices that we exponentiate in this way, and we find certain structures. And if you think a lot about these structures and what they mean, I should have made a little more space for me, but the way to think of it, so this rotation you can kind of imagine just as being described as a circle. We have some coordinate plane, and for every point on the circle, so there's a 1-to-1 correspondence for rotations in 2 dimensions and points on the circle. So if we have, for example, this point, we call that, we consider the angle to be 0. We call that the identity. And here is this point, I should say, is we describe as a 90-degree rotation, pi over 2 rotation if you prefer, and so on and so forth. So when it goes all the way around, it repeats. So this actually forms a kind of group because you have an identity. I've talked about groups before. You need a set with a binary operation. I'll just say binary operation. And you have these 4 principles. You have the identity. I'll just write ID. You have inverses. You have, what's the third thing? You have closure. And the fourth thing that you need for a group is associativity. So all matrix algebra in general is associative, and all maps in general, functions in general. Composition of functions, composition of maps in general is associative. Okay, so if we're describing things with matrices, then that is, we already have associativity. And by the way, just so you know, this business of talking about a group and describing it with matrices is called representation theory. So that will come up sometimes. So it's a big area of math, representation theory. So, but often we start describing our group with matrices to begin with. So we're already kind of doing representation theory from the get-go. Anyway, so as it turns out, the exceptional Lie groups are not associative, and so that's kind of why they're called exceptional. So they're sort of an oddball in math and part of many great mysteries in math that I'm pretty sure we do not fully understand what is going on completely with the exceptional Lie groups. We do know quite a lot of things, but I don't think we've fully understood the significance of them. Okay, now closure. So in this particular example, any rotation in 2D will, composition of 2 rotations will be another rotation, right? If you do 1 rotation and then a second, that corresponds to, so for example, if I do first this 90-degree rotation and then I do something slightly more than 90 degrees, that will mean that I'm basically starting here and then I'm doing this other rotation, which puts me over here. See? And it doesn't, the order here doesn't matter. So I could do this one first and then this one, or vice versa. Anyway, so you do 2 rotations in order and you get another rotation that you could have just done in one go. Does that make sense? So that's closure. And here the binary operation is, what we're talking about is rotation, or alternatively, you're talking about multiplication of this specific matrix. The set, what is the set? Maybe, it depends on how we define things, I guess, but maybe it's just the vector space R2, elements of the vector space R2. The ID is, the identity is rotation by 0 degrees. It's also the matrix. The identity matrix is 1, 1. This is the identity matrix. And all of these rotation matrices will have inverses. All you do is you change the matrix into being this opposite one that rotates in the opposite direction, and it will undo it, meaning that for every element, you have an inverse where, let's say you have an element A in the set, and you multiply it times its inverse, you will get back the identity matrix. It goes back. It's the equivalent of a 0-degree rotation, basically. So for every element in here, and I haven't proved it or anything, but I'm just trying to show sort of the intuitive story here. For every element, we have an inverse. That's second requirement. We have the identity within the set. we have closure, we have associativity. We started with a set, we talk about a set, we have a binary operation, so we have a group. In this case, it's a continuous group, it's not a discrete group. And we call this a Lie group, actually. So there's this whole study of Lie groups, and it's pretty interesting. And it's also interesting that it just sort of breaks down into a rather manageable number of families. So let me just describe these families here, okay? Now, you'll notice they have two names. There's an A sub n and there's SU's name. The A, B, C, D refers generally to the Lie algebra. Is that correct? Actually, that might be wrong. There's a lot of juggling around of different ways of talking about things, because there's these Dynkin diagrams, and then there's Coxeter systems that are closely related, and there's the Lie algebras, and there's the Lie groups. So never mind that. But okay, so we have these SO groups, SO2n and SO2n plus 1. So these 2n ones are the even ones, even dimensional, and these are the odd dimensional ones. And this is actually referring to rotation. So this group that we described here actually is SO2. It's the group of rotations in 2 dimensions. So SON is the group of rotations in n dimensions. So of course, it's important and interesting to study this in different numbers of dimensions. Particularly, one thing that's interesting to note is that, so in 2 dimensions, we need one parameter. Call it phi or whatever you want, theta. We need one number to specify a rotation in 2 dimensions. Well, how many do you need in 3 dimensions? Some of you will know the answer right away. Some of you maybe haven't thought about it. If you've never thought about it, go have a think. How many parameters do you need for 3 dimensions? And then, well, how about 4 dimensions and 5 dimensions and 6 dimensions and so on? Well, it turns out, I'm not going to explain it in huge detail, but for example, in 3 dimensions, here's the identity matrix. Just imagine zeros being filled in elsewhere. It kind of corresponds to this number of these entries that are up. I mean, you could look at this corner, this sort of upper triangular part, or you could look at this part, but not both at the same time, because with these rotation matrices, it has to do with the determinant being 1 and this kind of stuff. But they will be what's called antisymmetric. So actually, all rotation matrices of whatever n dimensions, let's say like 4 dimensions, for example, they don't have zeros, sorry. They're going to have a hold on. There are general matrices there's a formula for a general matrix that will give you any kind of rotation, but usually you think of it as 2 dimensions at a time. So like, for example, in 4 dimensions, you might have, for example, this is for cosine, negative sine, sine, and then everywhere else is 0. This is in 4 dimensions. And this cosine, sine, negative sine, cosine exactly corresponds to this sort of thing. So it's the same thing as rotation in 2 dimensions, but you have this identity matrix up here, and you have the rotation up here. But anyway, so spoiler, I guess, that in 4 dimensions, the way you count how many degrees of freedom the space of rotations is by counting how many entries there are, how many slots. And so there's 6. So you need 6 parameters to specify a unique rotation in 4 dimensions. And it continues with the same pattern as you go to higher dimensions. And so basically, it works out to n choose 2. But anyway, so that describes, we've done half of the classical simple Lie groups already. There's the even special orthogonal groups. So the reason they're called special orthogonal, special means the determinant is 1. So what that means is, should I explain all of that stuff? I don't know. Well, yeah, I won't go into the detail about that. I'll consider that a prerequisite if you want to know what I'm talking about right now. That special refers to the determinant being 1, which is always going to be true when you're talking about a rotation because there's no scaling going on. And if there's no scaling going on, that means that the rotation has to be, the determinant has to be 1. The orthogonal part is basically that, when you do some kind of, this is stuff I'm going to talk about later, when, let's say you have some arbitrary orientation, right? Some arbitrary rotation in, or let's say orientation in 3 dimensions, okay? And then you transform it into some other arbitrary, I can't draw it very well, what I got in my head. So let's just do like this. Let's say that this was X. Should I label this Y and this Z? No, that would be horrible. Demons would come crashing down from the sky to attack me. This needs to be Y. Oh, wait, am I doing this right? I think it needs to be X, Y, Z. Hold on, let me get my, I think this is good. It's a right-handed rule. It's a convention that we label things this way. So I'm imagining these vectors as pointing away from me. So I don't know. Maybe I'll get the right-handed thing mixed up or something. But anyway, the point is you have some transformation. Basically, it's a rotation from one unique orientation to another unique orientation. We can call this a map also, if you want. It happens to be a linear map, so we can call it a linear map, a linear transformation, a rotation in 3D, a linear transformation of a 3-dimensional vector space. You can call it all of those things. And what was the point that I was going to make? I actually forgot my point. Something about an n-dimensional vector space. Orthogonal. So orthogonal means that basically if you had an orthogonal basis when you started the transformation, you will have an orthogonal basis after the transformation as well. So it keeps those, but it could, for instance, switch it from being a right-handed chord system to a left-handed. So it could sort of change the chirality in a sense. So like if you had something that was winking with the right eye, it could change it into winking with the left eye and so on. It could change a right-handed person into a left-handed and so forth. So that would still be orthogonal because the output basis would still be orthogonal. Okay, but something that shears, so it takes an orthogonal basis, which normally a basis is orthogonal, but there are contexts, like in general relativity, where we talk about bases that are not orthogonal. Orthogonal just means perpendicular, right? More or less, that's what it means. And so we do a shear transformation, will change it. Like, for example, like this. That I want that one to be a little straighter. X, Y. That's a shear transformation. and that would not be an orthogonal transformation. So that's what's meant there by special orthogonal. Then you have the special unitary group and the symplectic group. Okay, so now for instance, SU2. So you see that this is SU something. It's just n+1 because it needs to be. Well, it hasn't said what n ranges over. I don't spend much time personally thinking about if it makes sense to have SU0 or not. You'd have to ask a mathematician. But let's just talk about SU2. SU2 is going to be where you have. You know what? Before we talk about SU2, let's talk about this other group here, which is the GLN. So for some reason, this is not counted as a Lie group, which I'd have to think about why specifically. But this is another. It's definitely a continuous group that we care a lot about, called GLN. It's described here as a type of matrix Lie group. So let's talk about that first. So what is GLN? So GLN is, it basically just refers to vector spaces, specifically the transformations that you can do on vector spaces. Okay, so it's like all the possible matrices in a vector space, basically, except that we only look at the invertible transformations, the invertible matrices. So, for example, if you're in 2D, well, a general matrix will be of this form. We just have 4 entries, right? And I'm going to talk about just there's other ways to write this. We can write it like this. So this is GL2 over the reals. There's also, you can do GL2 over complex numbers as well. I'm just going to talk about GL2 over the reals right now. So it will be matrices of this form, specifically all matrices such that they are invertible. And so what does that mean? It means that the determinant is not equal to 0. Basically, when the determinant equals 0, for example, in this story here that I was doing, if you had a transformation where this collapses down into 2 dimensions, okay? So instead of this, it becomes some 2-dimensional plane. Can you imagine, like, for example, this z basis vector could be collapsed down into this into the xy plane. Now that is, you can have all kinds of matrices that describe that transformation. That is a legitimate transformation. I think that would be a type of projection, maybe. Definitely you can do projections, you can sort of project everything down onto this xy plane. But you could also do it onto the xz plane or the yz plane or any arbitrary 2-dimensional subspace of this 3-dimensional vector space. So a 2-dimensional subspace of the vector space just means any plane in the space that intersects with the origin. When we're talking about matrix multiplication or using matrices to describe linear transformations, you have to have that sort of intersects with the origin. Basically, what is the requirement again specifically? It's that vector spaces. I'm sort of blanking, even though I know this quite well. I'm just blanking. There's 9 requirements for a vector space, and one of the requirements, I think, is that there has to be a 0 vector. Basically because you need closure. You need something where or rather, you need sort of like a additive identity. So this 0 vector plus some arbitrary vector in the vector space should equal the original vector. So it acts as an additive identity, not as some kind of scalar thing, right? This is 0 as an element of the vector space, right? It's important to make that distinction. There's 0 as a scalar, and then there's 0 as a element of the vector space. And you can kind of imagine that if you're in 3D, for example, it's the column vector with zeros in the entries. However many dimensions you have that many entries. 4 would be like this, and so on. So that's the 0 vector, and it's important to make that distinction between just the ordinary number 0, which we think of as a scalar, versus the 0 vector. Okay. And so because you need that 0 vector, you cannot, basically translations are not linear transformations, because they move where the origin is, basically. Translations are not linear transformations. Now, there's a trick to achieve the same thing, but you have to increase the number of dimensions. It's a common trick known to game programmers who work in 3D, but I haven't really talked about it here yet very much. It's a whole other topic. But it's good to remember that translations are not linear transformations. And so, getting back to this sort of idea of collapsing this into a two-dimensional subspace, that would be one example where the determinant is 0. Determinant can be imagined as a parallelepiped that this whole story, so I'll briefly go over this. The story of linear transformations in 2 dimensions. So I'm considering this a prerequisite, but this is meant as review. So if what I'm about to say is going to have a lot of fancy language around it, but the concept isn't really that difficult. But it should be a prerequisite. So if what I'm about to say sounds like complete nonsense, you need to go watch, for example, 3 blue, 1 browns video on the determinant, for example. Anyway, but as a quick review in fancy technical language, so if you're in a 2-dimensional vector space, you can think of yourself as starting with a orthonormal basis, and you're transforming it into some parallelogram. Basically, all possible parallelograms are valid representations of a linear transformation. Where, for example, this could be y, the new y and x basis vectors. Hold on, I got a cough. Hold on. Or even, these could be switched. It could be x and y here, where this was x and y over here. These are little vectors, okay? But you can think of it, there's like this square that you start out with, and then you're transforming it into a parallelogram. This is what's meant by a linear transformation. If it transformed into some other shape, for example, if some arbitrary quadrilateral, imagine these are 4 vertices, this is not linear, and I don't know what it would look like. There's other transformations that are not linear, like changing everything, let's say r, like everything, the distance from the origin is transformed to r squared, for example. That's a non-linear transformation. But the linear ones you can think of as mapping these unit squares that you start with to arbitrary parallelograms. So it's almost like this alchemy or calculus of parallelograms, basically. And further, you can actually think, well, every parallelogram is actually 2 triangles, and this unit square that we started out with is also you can look at the triangle there instead. This triangle actually is called has another fancy name called a simplex, and we can sort of generalize this into n dimensions, and we talk about simplices. But so I tend to think of it as sort of this alchemy of triangles, basically. It's what kind of transformations can you do on triangles is actually, there's some correspondence there to kind of all of linear algebra as far as I can tell. So I think about that a lot. I think it's interesting. Nonetheless, this area of the parallelogram is going to correspond to the determinant. And that is a very important lesson from linear algebra, that the area there is the determinant of the matrix. And we know how to, there's very algorithmic ways to calculate determinants from matrices. So you can do that. So in the three-dimensional case, you have what's called a parallelepiped, sort of this three-dimensional version of the same story. So you'd start with a cube and then a unit cube, right, with x, y, and z vectors, unit vectors, and then you would transform them into this arbitrary parallelepiped. If you can't imagine what a parallelepiped looks like, it's like you take some parallelogram and then you just sort of extend it in the third dimension and you have a parallelepiped. But you can have an n-dimensional, I guess it would be called a hyperparallelepiped. And so in general, and mathematicians will also say in GLN to refer to all of the sort of, this kind of refers to all of linear algebra, but we leave out any transformation that is degenerate, we say. Like I was talking about before, where, for example, if you have a three-dimensional vector space and you have a transformation that sort of smashes the space into a proper subspace. So, for example, two dimensionals. In this example, it could have been also just flattened onto a line. Both of these unit vectors could be smashed into the y-axis, for example, or any arbitrary line that passes through the origin. All the lines that pass through the origin in this three-dimensional vector space are themselves proper one-dimensional subspaces of the vector space. And there's a zero-dimensional subspace, which is just the point at the origin. And I'm not sure if you call that a proper subspace, but the reason I'm using the word proper is because the original vector space itself is also a subspace of the vector space. But you wouldn't call that a proper subspace. That's the terminology used. Because the thing itself, that's just terminology. That's just how we do that. Because we often want to talk about subspaces that aren't the original thing itself. You see the same kind of language used, for example, in set theory. Like there's a proper subset. Because the set itself, the original set itself, is also a subset. And so when we say proper subset, we are not including that one. I'm not sure if the empty set would be included. I'd have to check. And here, I'm not sure if the zero-dimensional subspace is considered a proper subspace. I'm guessing yes. And then in that case, if you wanted to exclude that one, we often say non-trivial, the non-trivial subspaces. So a trivial subspace is the original, the trivial subspaces would be the original vector space and the zero-dimensional vector space, which every vector space has this zero-dimensional vector space, which is just it's the number zero, basically. It's a vector of length of is it even a one? Can you even write it like this? Yeah, because this would be a one-dimensional vector, right? I don't think you can. So anyway, these when you have the determinant is 0, it will always sort of collapse into some proper subspace. And we call that often a degenerate transformation or degenerate matrix. And that also means that if you have that situation, the matrix will be non-invertible. Because if you're collapsing down into some plane, how are you going to invert that? Like many different points collapse to the same point. It's a many-to-one mapping, right? And when you have a many-to-one mapping, there's no clean way to invert that story, to go back in every case. If you somehow remembered where, well, no, because there's, many-to-one. So which one should it go to, right? We don't know. So that's a non-invertible situation. And so if you want to specify the transformations that are invertible, you say that the determinant is not equal to 0. Okay? So that's what GLN refers to. It's the n-dimensional. So as a set, again, it's a group. So as a set, it will have all of the n-dimensional linear transformations of it will have all the transformations. Let me start again. It will have all of the linear transformations of the n-dimensional vector space. Okay, so as a set, that set of transformations is the set. The binary operation is multiplication of matrices. Put a little m. That's weird notation. I should write it out, but I'm just saying it. Multiplication of matrices. And think about the 4 requirements. Identity, inverse, closure, and associativity. Again, matrix algebra is associative. So we get that one for free. Okay. And again, you can talk about GLC. I've never really thought much about it, but how about GL2H, where H is referring to quaternions, right? So we have vectors that are like Q1, well, should I say Q1? Yeah. Q1, Q2. So these are 2 different quaternions, and we're talking about all the possible transformations of this it's a 2-dimensional, but it's not 2 real dimensional. It's 2 quaternionic dimensional. It's a 2 quaternionic dimensional vector space. So what goes in here? Does it all make sense? I don't know. I haven't really looked into it that much. I think it does make sense. And I think that this would be SP2. So here we had, SPN, the symplectic group. And I think that's what that is. It's about transformation of matrices, transformation of sort of quaternionic vector spaces. And this SUN is transformations of complex vector spaces. So in the 1-dimensional case, you have a 1-dimensional matrix, or a 1-by-1 matrix of complex numbers. I guess I'll use Z. But that's just, when we talk about transforming a complex number, what does it mean that this is a 1-by-1 matrix? What does that mean? It means that we can just treat this like a normal number. So we're just talking about transformations of Z in general. And that is basically going to be that we're talking about functions on Z, which is an area of study, this study of complex functions. Very interesting in its own right. But so that would be, hold on, SU1 is basically this. So this the whole story of complex functions. So SU2 is going to be where you have vectors that have two complex components. Let's just say alpha, beta, right? SU3 will be where you have alpha, beta, gamma. You have three components, but they're complex. So talking about, that's my gamma right there. Talking about a three complex dimensional vector spaces, or just talking about complex dimensional vector spaces in general is complicated. If you're interested, look up Mobius transformations. So Mobius transformations are going to describe all the transformations of this two complex dimensional vector space. I want to get rid of this because it's not pointing there. Mobius transformations are for the two complex dimensional case. And you can use a matrix to represent them. They're very interesting. They're amazing, cool things. But that's just SU2. And there's an isomorphism between this and this other group, which doesn't show up. And I need to learn more, like why this wasn't listed among the classical Lie groups. But there's I guess it's because of isomorphism. Because this is isomorphic to... I'm writing the congruent sign, but on an angle there. This is isomorphic to spin 3. So the story of spinners that you might have heard of in quantum mechanics and all that. So this is like this whole story of Mobius transformations, and so transformations of a two complex dimensional vector space. This is the story of basic quantum mechanics that you learn. Usually the first thing you learn in a quantum mechanics course, not necessarily the double slit experiment, but more the talking about spin of an electron and the Stern-Gerlach experiment and that kind of stuff. So all this is that. And then SU3, which is here, this description of a three complex dimensional vector space. This is the story of the strong force. So actually there's all of, if you study this in quantum mechanics, this is all of electromagnetism basically. And then this is all of the strong force, strong nuclear force. Okay. So what I'm saying is, if you master Mobius transformations, then in some sense, you can take that knowledge and then map it all in the casual sense. You can map that knowledge to the whole, like all the information in a electromagnetics or an electromagnetism course. So, but that would be hard to do. It's not a bad idea. Like learn Mobius transformations, study Mobius transformations, but they're complicated to think about, but they're very, very interesting, very rewarding to study. And then look at electromagnetism. It's not going to be immediately obvious like how to sort of translate that knowledge. But that's something like that's on my to-do list. So yeah, and then so you need to learn that stuff, and then you go to the quaternionic case, and it's a whole new can of worms, and that's very, very difficult to begin thinking about. But I would start just about thinking of functions of quaternions, so transformations of a single quaternion to another quaternion. We'll just label it with a 2. Yeah, so that is, we've talked about all of these classical Lie groups here without specifying them in technical detail, but just sort of overall, we've sort of discussed them in an overall way. Now, note that the complex numbers and the quaternions came up. The real numbers are also important here. And there's one last number system that becomes important, and that's the octonions. The octonions are like, it's like you went from complex numbers to quaternions. There was this big step up. You can go another step up to the octonions. They're 8-dimensional, and they are useful in describing these 5 exceptional Lie groups. In some sense, so G2 here is what's called the automorphism group of the octonions. It more or less means that it's the space of ways that you can transform octonions, more or less. One octonion into another. And then F4 is sort of the complexification of that. So what you do is you do the direct product, I think, with complex numbers. And am I getting it right? For complex numbers, E6 would be, I think I said that wrong. I think E6 is the complexification of F4, and then E7 is like, you, instead of complex numbers, you use quaternions, and then E8 is like octonionic octonions. It's octonions direct with a direct product with the octonions. It's weird. It's very, very complicated and weird and difficult to wrap one's head around these exceptional Lie groups. But this is like a semi-obsession of mine, because these octonions seem to be important in physics, but the story is not fully understood yet. And I think, this is my personal opinion without being an expert on this stuff, I think that if string theory hadn't come along first, if we had discovered, well, we knew about the octonions for like a good 100 years prior, but nobody had really succeeded in drawing the connections between octonions and physics. But eventually those connections were discovered. However, they were discovered after string theory. So string theory kind of stole the limelight. And string theory has been perhaps a disappointment to most string theorists, I think. Whereas I think the octonions are very promising. Even Sir Roger Penrose, has been looking into the octonions lately. Since the pandemic, he says. And I think they're very promising. I think they're probably part of the answer to unification in physics. And I'd rather study them than string theory, although there's an enormous amount of sort of overlapping mathematics between the study of octonions and string theory, particularly this whole discussion of Lie theory is sort of the starting point for this deeper unification stuff, including string theory. I mean, string theory has a lot of... String theorists are talking about these Lie groups all the time. It's like part of the everyday language for them. And for most people studying unification physics, basically this is the major prerequisite. Just part of the language that they're using. Okay. So I will in the future talk about octonions. I think they're really interesting. A little complicated. They're the step up from the quaternions. So the quaternions are sort of 4-dimensional, and the octonions are sort of 8-dimensional. And then there's this discussion of Lie algebras, which there's kind of an almost one-to-one correspondence between Lie algebras and Lie groups. So it's a whole other can of worms, sort of, but there's this connection between them. And so I'll kind of describe the connection here. And I didn't even get into all this stuff that I wanted to talk about. I've talked about this in past videos. I'll do a crash course on this stuff, but first I want to say briefly like the connections between Lie groups and Lie algebras. So we described this Lie group that you can imagine as a circle. I'm imagining it kind of in 3D here for some reason. I don't know why. But there's a circle, right? Because when I think of 2D rotations, you can sort of map it all to points in a circle like I talked about before. And there is this tangent space to the identity. Okay, so here's a tangent line to the identity, which is right here. Here's the identity. I don't know why I'm drawing this like slanted or something. I think it's because I want to maybe perhaps talk about the three-dimensional case. But we're in 2 dimensions here. There's a tangent line to the circle at the identity. And this is sort of the intuitive picture I have in my head, that we imagine the identity is the matrix, the identity matrix, of course, and that we can talk about this tangent space as, for example, if it were 3-dimensional, there'd be more vectors coming out. There's like a tangent space. Here in 2 dimensions, there's really only this second vector. We only need one vector to describe this tangent line. Because if this is v, or I should say maybe, let's call it t. It's a vector, but it's t. Okay, I'll draw a little thing to say, actually it's a unit vector, okay, t. If s is a scalar, and we have st, this is scalar multiples of t will give us any arbitrary point in this tangent line. That's called the span of the vector. The span of the vector defines this one-dimensional vector space. But if we're in 3 dimensions, so the 3-dimensional picture here is just rotations in 3 dimensions. So you can imagine instead a sphere. And so basically, if you're choosing an arbitrary rotation in 3 dimensions, how do we do that? Well, we take an arbitrary line that we call the axis of rotation, and then we rotate around this axis, right? So take any line, and we kind of imagine that we've chosen a coordinate system, and we have this line goes through the origin and all that, because we're doing linear algebra here. But so any arbitrary line in 3 dimensions, call that the axis of rotation, then define some amount of rotation. Let's call it, should we call it theta? Not sure yet. But so any point on this sphere, okay, can represent a axis of rotation. There's a 1-to-1 correspond. Well, there's actually a 2-to-1 course. Oh wait, hold on. Yeah, there's a 2-to-1 correspondence between points on the sphere and axes of rotation that we choose, right? Because there's the point, and then there's the opposite point on the sphere. It's actually called an antipodal point. And both of those represent the same axis of rotation. But one will have positive rotation this way, and the other one will have positive rotation defined in the opposite direction. So whether you call that 1-to-1 or 2-to-1 kind of depends on what exactly you're talking about. But anyway, so there's this correspondence between points on a sphere and choosing an axis of rotation. And so points on the sphere, that's a 2-parameter space. We can think of it like on the Earth. You have longitude, latitude. You need some, I don't know why I'm drawing again, but here's the Earth. And imagine there's like this axis going through can we draw a line? Yes. There's this axis going through the North Pole to the South Pole, and then there's this so you have like this azimuthal angle, it's called, and you have the whatever the other one was called. But anyway, it's like longitude and latitude. You need 2 parameters to specify one point on the globe, one point on the sphere. That's your axis of rotation. Then you have a 3rd parameter, is your amount of rotation. But at any point on the sphere, there's this two-dimensional tangent space that's tangent to the point. And so we kind of imagine that this is just very broad, intuitive picture here. But kind of imagine the Lie group is this full space. It's a topological space. And the Lie algebra really refers only to this tangent space. And so it turns out that we only need the tangent space to really define the rest of it. If we define what these infinitesimal changes from the identity look like, that's enough to define everything. So instead of talking about Lie groups, we can talk about just this, what happens near the identity in infinitesimal amounts. And yeah, so that's a very linear picture also, right? And that's why the whole linearity of all of this is what allows us to all this machinery to work, really. So it's kind of discovered, well, you can talk about Lie groups, or you can talk about Lie algebras. And this is just not a thorough explanation at all. I'm just trying to give a taste. But there's not exactly a one-to-one correspondence between where you would hope, okay, maybe for every Lie group there is one specific Lie algebra and vice versa. But actually there is, for example, SUN, and also, I didn't even talk about SLN. So just like you have GL. GL was the general linear group, which is referring to sort of all the, we talked about it, GL. Where's GL? Right, these were all the non-invertible matrices in that n-dimensional vector space. It could be over the reals, over the complexes, potentially over the quaternions. I'm not certain about that. But when you go from GL to SL, now you're just talking about special linear group, and the special means determinant equals 1. That's all. Okay. And that's particularly interesting over the complex numbers SL2C. Is of particular interest. It's rather complicated as well. But anyway. So, I'm not sure why SLN was not listed among the classical Lie groups. I have to, like, when I was obsessed with this stuff originally, I was just trying to understand all this language. What is meant by SLN? What is meant by SUN? What is meant by this and that? So I haven't thought too much about, like, why in this list that we were looking at, why is SLN not in here? So I need to look at that, be able to explain that. Anyway, that's a thing, SLN. And again, similar to GLN, it can be, there's this other notation like GL something on reals or complexes or whatever, similar kind of notation. Something here. So I forget why I was talking about that. You would hope that there's this one-to-one correspondence, that for every Lie group there's a corresponding Lie algebra. But with SLN and SUN, both of these are described by the same Lie algebra. So yeah, there's a bit of detail there. Okay, so after you learn about Lie groups, then, or some people do it the other way. Some people learn about Lie algebras first, because you can actually learn about Lie algebras having no idea about all the story about groups, I think. Which to me is weird, because I learned some stuff about Lie groups, right? Stuff I've talked about today. I'm not an expert. But I am going to be working through this book about, and I'm not in Hong Kong, I changed that, so it doesn't show my friggin' zip code, thank you, Amazon. But I'm working through this book, which I own. It's tough, but it will inspire me to make some content. I will try to make some content talking about Lie algebras. It's very deep, this study of Lie algebras. It's very deep, very important for physics, I'm sure. Very interesting in mathematics. And this Cartan is hands down now my favorite mathematician. He's the guy that really brought all this together, even though it's named Lie after Sophus Lie, who kind of came up with this idea first. It was classified mainly by this guy named Killing, this German guy, but really the final work was finished by Cartan. Élie Cartan, amazing mathematician. His complete works you can find in university libraries. Sometimes it's like 4,000 pages. It's huge. And it's mainly in French, a little German. So that's what I'm going to be doing. That's part of my motivation here, that I want to dive deep into Lie algebras to give you a better, full understanding of this deep subject of Lie theory, which is very, very connected to physics and very important for advanced mathematics. Okay. To wrap it up, I was going to do a serious crash course in explaining all of this. Okay? I've done this before, but the whole video was an hour, and I hope to do this in like 10 minutes. So it's a real crash course. So there are prerequisites. It's not going to be simple, but I want to do it. So, but if you're stopping watching here, thank you for going through all of this. If you have any questions, please leave questions, because that will motivate me to make more content. If people are asking a lot of questions, I'll be like, oh, okay, I'll make a video about that. So that would be wonderful. Okay. So this is the Taylor series up here, and it's a way of approximating a function. So we have f of x equals f of a. So imagine you plug in some a. You want the function, you want an approximation of the function at a specific point. Now, when I say approximation, we kind of imagine that if we did this process ad infinitum, forever, that we would get the actual answer in some sense. Yeah, I mean, we need, like, if you have cosine or sine, we need some way to actually calculate that. And this is, I think, the way that it's done. So, but to simplify things, kind of let's imagine in our heads that we're sort of plugging in 0 here for a. So you're approximating the function, and again, that's sort of code for calculating the actual value, really. When I say approximating, this is like the way to calculate a lot of things. Anyway, let's work through this a bit, and in our heads, we're imagining that we're plugging in 0, just because that's the easiest, most obvious number to plug in for a. But it could be any number if we want to evaluate the function at a specific number. But so what we do, and this is for any function apparently, we, keeping in mind a function, it's like it can be many to 1, but it cannot be 1 to many. Is that correct? Did I say that right? 1 to many. So if you have, it's like you have all kinds of inputs, and for every input you have one output. You don't have multiple possible outputs for one input. Right? That's the concept of a function in general. We also, I don't know that there's really a difference between when people say maps versus functions. I think it's the same thing. But there might be some technical little difference. So we plug in 0 here. So we're evaluating this function at a number. Plug in 0 into the function as usual. Now here we have the derivative. We have x minus a. Okay. But the pattern here is that, for example, for the third one, we have the third derivative evaluated at a over 3 factorial times x minus a parentheses to the third power. So that's the pattern. In general, the nth derivative evaluated at a, well, with a plugged in, over n factorial, blah, blah, blah. Okay. So when you plug in 0 to different functions, you get these what's called Maclaurin series or Maclaurin expansions. And so you can stop and have a think if you'd like. Look at that. Look at the beauty. This one's nice because it comes out to 1 plus x squared plus x cubed, blah, blah, blah. That's kind of nice. This is probably the most important one of all, the e to the x expansion, Maclaurin expansion, Maclaurin series. So again, you take the Taylor series for e to the x. It's a good exercise. I'm not going to do it here today. I've done it previously here. But use e to the x and do all this. Remember that the derivative of e to the x is e to the x, so it makes this whole exercise easy, especially if you're plugging in 0 for a. So this is really the first one to focus on the most. But then cosine and sine are kind of similar, like where this is basically the term for the same term in cosine. Then we have the same kind of term that is in sine, because 1 factorial is 1. Then we're going to have a term like it's from cosine, except there's, up to sine. There's a negative sign, but so it's like term from cosine, term from sine, term from cosine, term from sine, and so on. So e to the x, in some sense, is like this. It's sort of like a combination of cosine and sine, except we know that it's actually cosine x plus I sine x. I've talked about this before on the channel, so that's a thing. Okay, so these are important for these sort of advanced things that are useful. Okay, so we've armed ourselves with these Maclaurin expansions, and then we try to do this. And what we do is we also define, where did I write it? We define that instead of 1, we can just write the identity matrix. Both of these are the identity. They leave things unchanged. Okay? We're going to use that. And because we're plugging in a matrix in here into the exponential, along with x here. So first I work out, here we're defining, A is this matrix specifically. So I just work out the powers of it. When you square it, you get this matrix that is, and this is a good exercise. Do this by hand if you want to. But you get basically the identity matrix times -1. That's what this is. And then here you basically get, well, because this is basically, this acts just like the number -1, basically. Which means that when you multiply this times a again, you simply get this with the negative switched, which is here. That's basically what a to the third power is. And then when you multiply it out, you multiply a again here, and choose right multiplication or left multiplication and stick to it. It doesn't, shouldn't matter too much which one. But you multiply this times a and you get back to the identity. And so then when we calculate a to the 5th, it's the identity times the original matrix. So it's just going to be the original matrix, and then a to the 6th is going to be this one. So it just repeats in this sort of period 4 repetition of matrices. And so because we're going to use that, this is the expansion of e to the x. I just copied it, same thing here as here, but now we're plugging in to x. We're plugging in x times that matrix a. I've labeled it a. Okay, so we're plugging in that everywhere. So what happens is we get this. It's a little messy, but okay. We've already calculated the a squared, a to the third power, and all that. So I've written it out here joyously. So we have again, so there's these factorial terms. So this is over 1 factorial, but I didn't write it. It's just 1. So we have over 2 factorial, over 3, 4, 5, and so on. We have x to the first power, x squared, x cubed, x to the fourth, fifth, so on, right? And these are, this is a squared, a cubed, a to the fourth, a to the fifth, okay? And so I just plugged in the matrices that we already calculated, that I just showed, and we get this. Yippee. And now we combine this into one giant matrix. By the way, I mean, again, here is the identity matrix, actually. This is the identity matrix. And so we're doing matrix addition now, so we can add this component-wise. So this is the addition of all the top left elements. This is all the top right, and so on. This is all the bottom right elements added together. So this is what we now have. We have e to the x times this matrix, or sorry, not times, e to the, well, this is the exponent. Okay. And it equals this big matrix. Again, just in case this is confusing to anyone, this is a big 2 by 2 matrix where this is the first element, second, third, fourth. So, but how did I get that? Well, let's zoom out here 1 notch. Let's do the top left element. We have a 1 to start out, plus 0, and then it's going to be minus x squared. So we had 1 minus x squared over 2 factorial. It's going to be 0 again, plus x to the fourth over 4 factorial, and so on. And the bottom right element works exactly the same as the top left element because they have the same exact pattern. When the top left is 0, the bottom right is 0. When the top left is 1, the bottom right is 1. So just copied that there. Let's do then the top right element. And notice the top left element is also very similar to the top right, except it's just the negative of it. Okay, so but let's do top right. So we have, this is again the identity matrix, so it has a 0 in the top right. Okay, so our first element in the top right is x times 1 right here. X times 1, which is x. Then we have x squared over 2 factorial times 0, so we ignore that. X cubed over 3 factorial times negative 1. So we have minus x cubed over 3 factorial. 0 for the next term. Then x to the fifth over 5 factorial times 1. So it's a plus. So this is all a good exercise to do yourself and really exercise your Maclaurin series and your matrix multiplication and thinking about all this stuff. It's good to sometimes do this. Some of you might want to go out to maybe x to the 6th and x to the 7th just to make sure you fully get the pattern. But I've only done it up to that where I've done it. And okay, well, have we made progress here? Well, we go back to these Maclaurin expansions and we try to make sense of what we have found. And we actually, if you're paying attention, you will see that we actually have cosine and sine given to us in this matrix. Specifically, this is identical to cosine. These are identical to the cosine Maclaurin expansion. And this is identical to the sine Maclaurin expansion, and same here, but with the negative sign. So what we get, and I guess I didn't write the final answer here. No, wait, what? Cancel. But that equals, So we have cosine up here, cosine here, sine here, negative sine here. So it's what I wrote to begin with. Where's that? This, with all this notation everywhere. That we can exponentiate x times this matrix and we get the rotation matrix in 2 dimensions. I think that's amazing. I think for me this is the motivating example for studying Lie theory, that like this is a big light bulb, says, wow, this is important. Are there more things like this? That, to me, that's amazing. I've talked about this before. You can watch my other videos if you'd like. There's going to be more videos in the future. I guess that's it for today. Thank you very much. Have a good one.